इनका mic थोड़ा दे दो.
Oh, mic.
इनका mic.
Mic is there.
This one is on and off. Yes.
Yes. Yes. Hey, তারপর পেছনে লাইটগুলো অন করে আর কাল থেকে লেট করবি 8:15 মধ্যে এখানে থাকবে লেট করবি You guys need that? I mean, if you need that. Sir, recording. Sir, recording on sir. Should we start? 8:39, 40. Start. By the way, it is your responsibility. Every day you will do that. And come before to set it up. And is it the same link? Not the same link भी होता है ऐसा नहीं होता है. You can. Then I have to send them the other link also. This send. नहीं ठीक चल छोड़ दो तो हर रोज नहीं मैं थोड़ा करूँ
हाँ करो इधर भी कर सकते हैं
हाँ
इधर रिकॉर्डिंग
बस मुझे ये घुमाना है और जूम करना है ये व्यू फाइंडर है क्या नहीं
हाँ फिर
ये है व्यू
आ जाओ
ओके नहीं ठीक है स्क्रीन ठीक है स्टार्ट कर दीजिए ये है ना स्टार्ट
हाँ रिकॉर्डिंग
छोड़ो वी कैन स्टार्ट कहाँ है सर स्टार्ट कर दीजिए स्टार्ट हो गया सो फ्लो आई थिंक वी कैन स्टार्ट
Okay, is it working?
यस
Okay, so hello everybody. Welcome to the second lecture we'll continue on treewidth today. So the idea of today's lecture is to review how to use tree compositions to design algorithms for some graph problems when you are given a 3D composition, of course. Alright. Okay. Maybe just very briefly, without details, I'll tell you just one detail because we are talking about algorithms. So we'll assume that we are given the 3D composition. So the problem being that, okay, how to find the 3D composition? That is not necessarily easy because, well, finding a 3D composition is always easy. I mean, you can take a single bag in a tree of size 1, which contains everybody. But of course that is not optimal. So finding an optimal 3D composition where the width is optimal and it's small, that is challenging. In fact, deciding, deciding tree width is an NP-hard problem. A tree width of a graph that knows some this is NP-hard. Okay, so we don't even have a hope for finding a polynomial algorithm to compute a good tree decomposition. However, there are workarounds. So what people do, okay, one thing is, first of all, if you are interested in practical algorithms, so if you want to implement it, there's a very simple heuristic which actually gives you a tree decomposition. It is not optimal, but in practice it often works well and it's easy to code. So if you're interested in coding that, so this is called the min-degree heuristic. Min-degree heuristic. And the idea is to try to, I mean, you have seen yesterday that the equivalence between partial k-trees and tree decompositions with at most k. So the idea will be to kind of see our graph as a partial k-tree. K is not fixed here. K will kind of arise from the algorithm, and we are just hoping that the algorithm will be good. So it's not good, it has no guarantee, but in practice it is not so bad. So the idea is, what do? You choose the vertex of minimum degree in G. So let's say B has min degree. Okay, and this we will try to see it as the last vertex that we have inserted in our K tree. K is not given, but for some K. Okay. So what do? These are the neighbors of B, and what we are saying is that, okay, let's say that this was our, Vk. So sorry, Vn, where V1 up to Vn is my sequence of constructing the K tree. So this will be the K tree sequence. So essentially what I'm saying, okay, look, this is the last K, because he has the smallest degree, so I'm hoping that this will create a small bag, as small as possible. And this will be my Vn. Now, recursively, what do? Well, I delete this one. I make the neighborhood a clique. So maybe there were this might be an independent set, whatever. You create the clique. Just to be sure that it will be containing some bag later on, so that it's not split. Okay. Now we will be sure that later on, this is a clique now, and this will can be formed as a bag. And now you just repeat this. And in fact, what you're doing now is it's a heuristic, so you're seeing the graph as a partial K tree for some K. And you can backtrack and get your tree decomposition by just considering, this will be now a K tree, a partial K tree, and you just consider the bags of the K tree like this. So this is a practical algorithm for computing the tree width. So yeah, somebody who doesn't too much care about optimizing and so on, they can code this, and this is a nice technique. But the other technique that people are using is the following. So there is you can find, so this is not like, I will not go into technical details because I don't know the topic very well, but this is like a theorem that you can use, which is that there exists an algorithm for one can compute, so given a graph G and an integer K, one can compute. So we're given G and K, we want to find, is there a tree decomposition of width K? 3, 1, okay. Compute. By the way, I just forgot, but this is NP-hard. This is even NP-hard to approximate within a given constant. This is a very recent result. So this result is like 20 years ago. But last year there was a nice reduction by Euler, which shows that in fact it is even hard to approximate within some constant. And in fact there is even a result that, assuming some conjecture, you cannot approximate for any constant in polynomial time. But what we'll do here, we'll approximate it within a constant, but in exponential time, where the exponent only depends on this K. So one compute, then compute, one can either compute a tree decomposition of width k plus 1. Okay, so this kind of is, you can see it as a 2 approximation. Or decide that, or you can certify, you can find an abstraction to show that the tree width is too large. Or you should the algorithm finds an abstraction which proves that the tree width is large. And this can be done in time. Exponential in k, but linear in n. So this result is also quite recent. So here I can refer to the recent proof. There was an older proof, but this is, this is on archive. I'm not sure if it's published yet or not. This appeared very recently. And this is I think the up-to-date, one of the latest algorithms to do this.
This proof is a new one? Or?
So there is an old one and there is a new one from 24, which is simpler. The simpler, and the simplicity of that hardness actually implies the approximation hardness. It's a reduction from 3 7.
And this is for general graphs, is it?
For general graphs. In fact, it has been a long open problem for a long time, and I think it's still open to compute, to decide treewidth for planar graphs. I think this is still an open problem, if I'm not mistaken. So, for particular graphs, it might be interesting to study. Okay. So, alright. So, yeah, the bad news is we can't do much work with treewidth, but this is actually not too bad. In fact, for all practical purposes, that things I will show you today, this is actually good enough. This is actually good enough because you can use the algorithm. Anyway, the algorithms I will show you, they're usually exponential in treewidth anyway. So they will be useful only if treewidth is very small. And we can't, the problems we're going to solve today are NP hard in general, so anyway, we need some exponential component in our algorithm, and that exponential component will come from the treewidth. So this algorithm, which is exponential just in the treewidth, is not going to be a bottleneck for these techniques. So this is good enough. And okay, you don't get the exact treewidth, you get some approximation 2 times, but still this is fine. So there are also similar algorithms which actually don't give you this factor of 2 with a slightly higher exponent. Even if you want that, this also exists. So there is a whole series of papers. But I will not go into details of these techniques. I prefer to focus on how to use the tree decompositions to get our algorithms. But still, it is maybe important to know. This is there. So how to obtain algorithms given a tree decomposition. So the keyword, the main keyword, is dynamic programming. So for those of you who are familiar with algorithms, this is one of the standard techniques which was developed from the 50s, 60s in algorithms in general. It doesn't have much to do with programming as coding. So the terminology is from that time, which was a bit different. So what does it mean? Well, for those who are not so familiar with algorithms, it doesn't mean much else than essentially doing induction, you could say. So the idea is you take your problem and you prove some inductive formulas, which are based on simpler problems. So for example, you will minimize over, you will branch on different possibilities, and you will minimize over all these possibilities. And the idea is that this process is going to be exhaustive. You want it to be, having a good running time also. And so you will then solve inductively the problem, and then inductively, etc., etc., until you reach to a base case where the problem is very easy. So this is the general principle of dynamic programming. Right. But okay, what I will do, and I mean this is you know I think the usual presentation of this is to start for trees, because essentially this was also the motivation of introducing treewidth, is that we know how to get efficient and good algorithms for trees, and then the ideas for the treewidth are extensions of it. So we'll start with trees. I think this is useful, especially for those who don't know too much about algorithms. For the trees, it is much more understandable. Okay. So generally, the first problem that is shown, and I will do the same, is independent set of graphs. The reason that this is chosen is because this works very well, and this is very nice and easy to explain. Other problems are slightly more tricky, so this is, I think, a very good choice. So what's an independent set in a graph? Independent set. So in a graph, an independent set is a set of vertices S where there are no edges. Okay, among the set. Okay, independent set. Set S of vertices with no edges inside S. So, for example, if you take an empty set, this is an independent set. So, of course, we want to find a large one. So the goal is to maximize. Maximize the size of S. So we are looking for largest possible independent set. Okay. All right. So, in fact, for trees, there is a simple greedy algorithm which solves the maximum independent set. So the idea is not to look at that. So of course, greedy is always usually simpler than dynamic programming. But I will still show the dynamic program because we're going to extend that for 3D compositions. So the greedy, if you want to find an independent set, what could you do? I mean, you could take the leaves, because you know that, I mean, if you had taken the father of a leaf, you might as well take the leaf. There is no benefit of taking the father, especially when there are several leaves, it's even more visible. You take all the leaves, and then you know you can't take the father, you don't take it, and then you recurse. So this is a very simple greedy algorithm. Okay, by the way, many times when people study independent sets, whether it is on trees or, for example, on perfect graphs, it's a very famous problem which you can solve on perfect graphs. They usually, many times they're able also to solve the weighted version where you put weights on the vertices. Let's say you put some weights. And now the problem becomes more tricky, and this simple algorithm doesn't work. Because here, for example, it is not good to take the leaves. So the weight is, so I'm looking for the max weight, that means the sum of these numbers, which I select. So this is my independent set. Here it would have been 1 plus 10 plus 5 plus 1, etc. But here you can see that it's actually more beneficial to take the father, because the father has weight 20, it is much more than some of the children. So this simple algorithm doesn't work anymore for weights. So I will not use weights in my in what I'm showing, but it is very easy to extend to weights. So the techniques I will show do work even if you have weights. So what are we going to do? So dynamic programming on a tree. So the first thing is I'm going to root it. So I'm going to select any vertex of your choice and say that this is a root. So I have the notion of children of a vertex, so you have the levels of that tree. And so this is the child, this is the parent. Okay. Parent. these are children. Standard terminology. So basically the children are the ones which are more far away from the root, the neighbors which are more far away from the root of a given vertex. And what will the algorithm do? It will, sort of like this greedy thing, it will go bottom up. So I'll start at leaves, and I will compute some numbers, some functions, and each time I go one level up, I will use the children's functions to compute the father's functions. So this is the way we do dynamic programming on trees. So essentially what I will do, I will try to find recursive formula, inductive formulas, to express the largest size. So I'm looking for the largest size of an independent set of a given subtree. So let's say I reach this node V, this vertex V. So I'll compute this, the functions for this subtree as a function of the numbers for these children's subtrees. Really complicated subtrees. So assuming I have computed the children, I will now compute the father for this tree, and you can see that if I'm able to do that at every step, of course, I will reach the root and I'm able to compute the whole thing of the whole tree. So for independent set, what I will do, I'll just compute two possibilities. So in dynamic programming, what we want, we're trying to be exhaustive about what is happening at our local point of the dynamic program. So here what I call local point is just the current vertex that is visible. So I will define the following. So I'll make two functions. So I for independent set. So if you take a vertex of your tree, let's make this. So V star. So star, I'm putting star, it means kind of unrestricted. What is this? This is the largest size of an independent set. In TV, what is TV? My tree I am calling T. TV is the subtree rooted at V. This is root. This is TV. Alright, so obviously what I'm looking for is to try to compute in the end I of V of root star. If I know the function for root, this will be the whole independent set of the tree. But essentially, when you look at an independent set in your TV, what I want to see is what are the possible scenarios which are happening for V. And there are actually, for independent set, two important scenarios which can happen. First scenario is that I have selected V in the independent set, or I have not selected it. So I could do two functions, one of them expressing the fact that this is in and or this is out, but for simplicity it will be a little bit easier to not be disjoint like that. So I'm defining one function where I don't care whether it is in or out, and one function where when I definitely know it is out. Because if it is out, so if it is out, I know that, well, I can select these or I can't, but anyway, it's a little bit different. But if it is in, I know I cannot use any of the children. So it is in my set. I know that for the children, I definitely cannot select these. And that's why I will need the function which selects the children as out. So this is why the out is more important. Let's define it. So the second function I'm doing is, let's say out. I'm very precise to be very clear. So this is the largest size of an independent set in TV Okay? These are my two functions.
So why are you not defining a in also?
Because I will not need it.
Okay.
So I will write the formulas and
Okay.
I mean,
I see.
probably you can do also with in.
Yeah, yeah. But you need only one.
Formulas will be slightly easier if you
Okay.
do that. Okay. So maybe I can write formulas I want to convince you that they are true. Well, first of all, so there will be two cases, if there are children and no children. So if B is a leaf, so my goal is to compute these and with inductive formulas. If B is a leaf, it is very easy. Then I know that the optimal independent set, so the subtree rooted at that leaf is just a single vertex, just B. So if I don't care, I can just take B. So that number is 1. And otherwise it is 0. Because I'm forced to not take B, so of course in a single graph if I cannot take it, what can I do? It is 0. Okay? And otherwise, so let's say B has children. So if I know that my V is out, so I know that I'm forcing V to be out. So I want to express using the children. But then, since V is out, I essentially have no constraint on the children. So I can just use for the children this function, which is, I will take for the children the largest independent. So this will be sum over all the children of this function. Okay. But now, for the unrestricted case, I mean now it could be in or it could be out. So now the formula will look like this. There will be two cases basically in my formula. It will be the minimum over two things. So the first is I have taken B. So I'm paying 1 for B. I'm gaining 1. And I will take sum for all the children. Now that V is inside, I'm absolutely obliged to take the children out. Otherwise I will not get an independent set. Okay. So this is one case where I'm taking V and so its children are all out. So assuming I have computed the functions for the children, I can just write it like that, inductively. And, alright. Well, and in the other case, it is out, so I can just, I could repeat this, but I will just write out. Well, if you prefer, you just write the same form. Okay, so two cases, either V is inside my independent set, or it is not. Then the formula is this. Oh, max, sorry. Correct. So most of my research is on minimization problems, so I always get confused when I do it. So hopefully. Sorry? No, I'm just doing all independent set to make it simpler, but yeah, you could weight it very easily.
Instead of 1, you have to put the weight of
Exactly,
B.
you put the weight. That's the same. So that's why this is actually very powerful. So the weights are accommodated very easily. Okay. So I think the formulas are quite intuitive. But maybe we could see how to prove them. So basically, when you do this, I mean, okay, whether it is for trees or for tree width, the idea is, okay, you have to analyze your problem, you have to see what happens, what are the different cases. So you see, I analyze the different cases, in or out, but you know, then you can try to change the case a little bit for convenience. So you have to then write your formulas. So this is normally quite intuitive, but of course you have to convince that this is true, so you have to prove the formulas. And this task is sometimes a little bit tedious, but it has to be done, and sometimes you think that the formula is correct, but it is not. There are some corner cases that you forgot, or something like that. So this proof is actually important. It's maybe
So this one is for tree, not
This
tree
for trees.
decomposition.
what reasons?
Yeah.
Okay. Right. But by the way, just before we look at how to prove these formulas, what will be the running time of my algorithm? So this, in fact, now describes the algorithm, because what do? I start with a leaf. For the leaf, so I always, for every node, for every vertex of my tree, I maintain these two functions. So for the leaves, I have 0 and 1. And then I just, for knowing that I have computed for all the children, so I go to upper and upper in the tree, and if I know I have computed for all the children, I just apply these. And as you can see, these are just computations, right? So you have to, you can find the values which are stored in the children's vertex. I mean, you have to store your tree, of course, in a certain way. You have to be able to access these values. But you have two values for every vertex of your tree, and you just do the sum to this. And you have this maximum. So all of this is just numeric computations, basically. Okay? And like this, you proceed bottom up until you reach the root. And for your root, you have these two functions. Of course, this one is the one you're looking for. Yes. So what's the precise running time? So for every vertex, we have to look at we have to do the sum of all the children. So you could lazily argue that there are at most n children. So at each step you have at most n things to compute. So this will be a quadratic algorithm, because there are n vertices in the tree. But you can also observe that, in fact, what is happening is that you are, in fact, considering every edge of your tree once. So you consider this when you're computing this. You're considering this edge once or twice, I mean, constant number of times for computing a value. So that means in the whole algorithm, you will actually consider every edge constant number of times. So this is a O of n. Functions. Bottom up. And the running time since every edge of the tree is considered and of course there are n minus 1 edges in a tree, so okay. Going too much into details. Alright. Yes. So So if I want to formally prove these formulas now, well, I mean, for the leaf node, this is very easy. There's nothing to prove really. Just to argue that, yeah, the best you can do is take it or not take it, depending on the cases. But if you want to formally prove these equalities, I mean, it's an equality, so the best way is to decompose and to prove two things. So, at most part and the at least part. So, in this case, so I don't know, let's take one of them. I want to prove this. It's at least the sum. These, and then the second thing is most. So, what does it mean conceptually if you want to prove this? So this means we are trying to maximize our independent set. So this is a low amount. So in some sense what we want to show is that our optimum size of an independent set, where B is not in, is at least this. So that means the best is to show that we can construct such an independent set. So what this means is we can, or it's not we can construct, there exists an independent set of the subtree rooted at V, not containing V, independent set S. And we're doing also that B is not S of size this size. Now, so here the proof is very trivial. So by definition, what is this? This is the maximum size of a. So for every child, definition is still here. This is the maximum size of an independent set of the child node. Since I am requesting that V is not in the set, so I don't really care about V, so I can just take the union. So we know there exists an independent set of the child number 1, for example, of this size, and for the child number 2, etc., etc. So I just take the union. Take the union, and this is an independent set. Size okay. So you know by definition that there is such a set, even if we don't know it, but by definition there exists. So we take the union, and okay, why is this an independent set? For trees it's kind of trivial, but it is nice to see this reasoning because we'll transfer it to tree decomposition. And the reason why is of course because there is no edge between the subjects. Okay. So if you take S1, S2, S4, of course, because it is a tree, there's no edge here, so the union is, of course, an independent set. But this is important. It works because of that. And now for the most part, we have to show that we cannot do anything better.
So the greater than equal to comes from equal to?
Sorry?
The I, V out greater than equal to?
What is the question?
Yeah, that greater than equal to, yeah.
Yes.
So that, but there is equal to. From there you are saying that since is equal
No,
to.
I do two cases. I prove this first inequality, and now I do other inequality.
Okay.
I'm still with the same formula.
Proving the first formula.
Yeah, I'm just proving the first one.
Okay.
I mean, this one. Actually, I'm erasing it. This was the leaves, we don't care about the leaves. So I'm doing this one.
The first one.
Okay. I will not do this, I mean, it's very
I
simple.
thought that is definition. That is not definition.
Definition is here. This is definition. This is definition, and this is formulas. you want, this is a lemma. I'm proving that lemma. Okay. So this is definition. This is something I want to show. I'm now proving just one. One I have decomposed into 1.1, which is this side inequality, and I'll do the other inequality. Let's go here. So essentially, I mean, to prove this, there is always a constructive part where you want to construct to show that one side is true. So in this case, this part will be a constructive part. You want to show that there exists an existential part. Constructive is true, but you want to show that there exists something of this size. And the other one is a bounding part where you show it cannot be better. So now let's do the cannot be better part. So what do we do there? So here what we will do, we'll start with a hypothetical independent set and which satisfies the property that V is out, and we just show that it cannot be bigger. So take S star, the largest independent set of TV such that V is not in the system. Okay. Okay, so children. 1, 2, 3. He's not there. And now it's kind of the reverse reasoning. So I have some independent, well, I know it is not, V is not in my independent set, but otherwise I know nothing about my S star. But I know V is not there. This is S star in pink. Okay. But now what you can, it's very easy to observe that, well, each of these is an independent set of the subtree of the child. So of course, this cannot be bigger than the largest size of an independent set of this subtree. So let's call this S1 star, S2 star, Sk star. So each of them is an independent set of the subtree, so you cannot be larger than that definition. So Sj star, Si star. So what is this? This is S intersection, S star intersection TVI. Okay, so it's the intersection of that S star in the subtree. Is an independent set of my subtree. So by definition, size of S star is at most by the definition. So of course, S star is the union of these. So the size of S star is the sum, is at most the sum.
S and star is subset of S star.
Sorry?
S and star are subset of S star. Is it?
Yes.
Or, I didn't get it.
Yes. So should be V of TVI if we are technically completely
Correct.
intersection.
We form returning the vertices. Star, move someone. Well, that is because S star is just equal to the disjoint union of these things, and they are all disjoint. And I'm not saying, but underlying is that yes, they are all disjoint. So this is the reasoning behind this type now we will see how to generalize this for different 3D composition.
Could you mention again why is it a linear time algorithm?
Sorry?
Why is it a linear time algorithm?
It's linear because so there's a linear number of edges in my tree. I'm claiming that for every edge of your tree there will be some constant number of computations. Because when you're let's analyze locally, so you are at vertex V. To compute this, you are accessing the children's information. But each of them has just two informations to check. Right? So you're doing this sum. So this sum will be nothing else than checking information as this, checking this, checking this. Maybe you have to access a couple of times, but constant number of times you access. So if you do a summation over all the steps, even though you have many number of vertices, still overall the number of edges being linear, it's a linear time algorithm.
So this A star is IV out equals to the cardinality of S star is equal to the
S
number
star,
IV out
yes, because by definition, yeah,
by definition.
yes, because yeah, it's true. I should have said that. S star equals to. So here you get so, alright, let's go now to the same problem but on a 3D composition. So we will have the same picture, we'll have this tree of our 3D composition. But now a node of the 3D composition is no longer a single vertex, it is a bag. So what will we do? So here what we did, we said that okay, is the V in or out? And what we will do now, we will actually check which subset of the bag is in and which is out. So if the bag has size k, there will be 2 to the power k possibilities. So instead of 2 functions, we will have 2 to the power k functions. This is the idea. And we'll try to find similar formulas. And the proof ideas are really similar. These two inequalities to prove, one of them being constructed and the other one showing the upper bound by considering an optimal one and deducing that these ones are also equal. But so I'm not doing the proof of part 2, but it is the same essentially. Well, there are 2 cases to consider, so it's a bit more long. The ideas are the same. Here. So now, remember the setting. I'm given graph G and T. The composition of G. Okay. So same idea, I'm looking at the tree, I'm rooting it. Yeah, maybe some, no, I'll first define, no, I need the notations first. So as before, TV for a node V will be the subtree. Rooted at V. Okay. tree of the 3D composition. This is TV. But now you write, I mean, this tree is not our graph, so one, I think, important picture to visualize what's going on is, well, you know, that this is in G. In G, this root corresponds to a bag. Okay. And then this one corresponds to another bag, and this has some intersection if you want the graph to be connected. So you have this picture. This two. Okay. So this is we are working with a tree, but in reality, what we're interested in is this picture. So what I will say that this subgraph, I'm calling it GV. So GV, what is it? Formally, it is the subgraph of G induced by the union of the bags of T. Union of X. So all the nodes which are in TV, I take the union of their bags. This gives me a vertex set. It is this vertex set. And I call GV this. It's just notation purpose. Okay. And really what we are doing, we are working on this, but we are doing things for that purpose. This is horrible. Okay. And now I will just define one function, but it is indexed by, so V is a node of the 3D composition. Okay. And S is a subset of XV, of the bag, V. So as I said, for every subset of the bag, there is one function. And there's one, you can see it as a table or whatever you like. This is the max size of an independent set of GV, an independent set. It's not too confusing. Maximum size. So let's call it a star. Star for optimality. Maximum size of an independent set. Oh no, this is. Let's say SV. GV. Which intersects our bag precisely in this S. Okay. So, actually, my picture is wrong. G, this is GV. This is XV, I think. Yes. This is, I think, this is V. This is XV. GV contains XV.
No, I think you were right the first session.
This is XV. This is XW.
Yes. Right.
So what I'm doing here, I'm taking my XV. So I don't care, you see, the graph continues upstairs, right? But I don't care about that. I'm just considering the subgraph, GV. They look like that, etc. But my S, this is S. This is some limited and this graph. So here I don't really care what's happening, but I force them to have no other, to exactly have as vertices of this bag this purple set S. This is what it is. So the idea is, yeah, so there is one such thing for every subset of the bag, and the idea will be to compute this using, like before, some inductive formula. Okay, and what's the formula? I want to show, I mean, it is a bit like before. So what I'm doing, so now I have fixed S, I know S is in my independent set. So what I have to do is that I will express it using these children bags and children GEDs. And of course they have to agree with S.
So my goal is to find the independent set of G.
Yes, but now it's like before in the tree, I'm fixing the node V.
The final goal is the
Yeah, my final goal is to find this for the root. And if you know all this, if you know for every subset of the root, you know all these functions, you just take this biggest one. Right? So if you know everything for the root, you're done. Good remark. So, and go the independent set of G, independent set of G will be the max over S included in the back of the root of this. Okay. So I'll just look at the root. I have a bag in the root. I look at all the possibilities of how this independent set intersects the root, and I take the maximum. I know my optimal independent set has to intersect the root in some way. Maybe it's empty set. I mean, of course, here I'm considering empty set. So this is the end goal. And the principle is exactly as before. I will just write some formula. And then it's exactly the same algorithm as before. I compute for the leaves, and I go do bottom up by these computations, and in the end I find my value. By the way, it's true, for the trees I forgot to explain that also using this you can actually compute the independent set, so I didn't mention that. But I was just talking about numbers. But if at each step you remember which choice gave you the maximum, this is just a small succinct information that, well, for two functions you have to remember, for the trees you had two functions, so you had to remember two maxima. Then once you reach the root, you can backtrack using this information and you can actually compute your independent set. So these algorithms are actually constructive, or can be made constructive. It's not just about computing the numbers. Okay. So what's my formula I want to show? Okay, maybe all the leaves. Well, in general, just one thing is that I will just say that this is undefined if S is not an independent set. So this is just by convention, because I will work with maxima, right? So I never want to take this kind of infinity, so I put it as minus infinity, just to avoid any trouble. If V is a leaf, this GV is just the bag, right? If V is a leaf, there are no children, so it's just the bag. So there is no real computation to do,
So now we are only trying to figure out what are these numbers. So what is IVS? That's all we are concentrating right now,
Yeah.
locally.
Yeah,
Okay.
exactly. I mean, just like before. In the
Yes, yes.
But as I said, this can be
It is a bit difficult, more difficult, of course.
We have bags now.
Yeah.
You just have to work with the bags.
We don't have that independent set disjoint union so easily.
Yes, but almost. I mean, that's the point. Okay, maybe it's a good way to explain the intuition behind this. So why this will work in some sense. So of course, you can see that now these bags kind of intersect. But remember, one essential property, which we didn't really prove, but anyway, it was also in the tutorial. So this bag is a separator. Remember that intersection of two consecutive bags are separators. So in particular, every bag, if it has children like that, if it has vertices, it actually forms a separator. So that means if you don't consider the bag, these things are actually disjoint. They are disjoint components of it. So this was essential for the tree algorithm to work, and this is also essential here. That because it is disjoint, the same principle will work. We will just have to be careful with this bag because the intersections happen in the bag. So for a leaf, so these are trivial for the leaf. I just have to check whether yes it is an independent set or no. I have no choice. My whole GV is the bag. So I have these. Either it is not an independent set, then I say there is infinity, otherwise it is the size of S. It's not a leaf. This is the more interesting thing. What is this? Well, count the vertices in S. But then I'll have to remove them because they might be double counted. In this case, for example. I'll do that. So again, like before, I'll do a sum for all the children nodes. So yeah, you have E and like before V1 okay. Children. Okay. Now for every child, what I'm doing, I'm taking the maximum independent set of that subgraph. Among all the subgraphs which agree with S. Sorry, among all the independent sets which agree with S. Let me write that formally. Max. So I'm taking the independent set for Vi for some S prime. So S prime now is a subset of this. Let's say. This is some back. But what I want is that this part, which is not the case here, agrees with my choice of this. So S prime should be this S prime should be a subset of I. Okay, and S prime intersection XVI. This is correct. So I'm looking at the subsets of my child bag. This is XB, some child bag. XBI, this was my S. So I'm looking for some like that. prime, whose intersection with the top bag, S prime intersection with top bag, equals intersection of my S of the that is fixed here with the child bag.
So S and S prime agrees on the intersection.
Yes, S and S prime agree naturally on the intersection of the two bags. Yes.
Here you have a question, I think. Flo,
Yes.
there is a question from someone. There is a question from someone.
Yes, I understood. I just
Okay,
want to
okay.
write it.
Oh, okay, okay.
So for leaf, that why it will be cardinality of S?
Because for a leaf, my subgraph GB is just the bag itself. I mean, the induced subgraph of the graph induced by the bag. So since I'm forcing in the definition to take an independent set which intersects exactly at S, there's no choice, I have to take S. Right? If you're, so this is by the definition of this. This is now my whole graph. So this is XB. I have fixed S. So essentially this definition is telling you you have no choice on this bag. You have to take S only. The choices come from what is below. If there is nothing below, there is no choice. This is what this definition is. Okay? Next other questions?
There may be multiple maximum independent sets. Right? Oh, but we are just computing for S. Okay, okay.
Yes, for every fixed, so I fix my S.
You fix your, yes, yes, yes.
So I take this, I take the maximum over all the S primes which agree with S, and then that is where the choices are. I could take any S prime as long as it agrees with S. And of course, in this tree continues, I mean this subgraph continues. Here I don't really know what happens, but I have computed by inertia. Okay, now of course this part has been counted twice. So I have to subtract. So this formula is not complete. Okay, so I just have to be careful not to double count it. I have to subtract this double counted part. Because I'm adding it once here. For any of the children, I don't want to add it. Okay. Is this correct? Well, of course these S primes should be independent. But that is, I believe, taken care of by this. So if S prime is not an independent set, it's minus infinity. It's okay. Alright. So now, okay, assuming this formula is true, the algorithm is similar as the one for trees. You go to a tree decomposition. You start with the leaves. For the leaves, it is very easy to compute these formulas. So be careful that now there are not two formulas. There is 2 to the power, I mean all the subsets of the bag. This is the number of formulas we have. So 2 to the power treewidth plus 1. Plus 1 because the bag says treewidth minus 1. Plus 1, sorry. Okay, and now same thing, like supposing that you have, assuming this formula is true, assuming that you have computed for all the children, you just apply the formula. Okay, now this formula of course is a bit more complicated because you have to do these kind of computations. But
for the non-fixed case, where are you considering the similar thing like for V out and V in?
we are considering it, it is essentially expressed by this. This tells you which, so V, like V doesn't exist in our graph, right? Our graph is this, right? So V is just something abstract that we are embedding our graph in the tree condition. So V is not very important. What is important is this bag. So S tells you who is out in. S tells you who is in. Those are not in S, they are out. So this is in fact acting like a partition of your bag into in and out. That's what it is. So it's really, and in fact this, maybe would have been better to say in and out for the first part. It would have been more close to this one. I think the formulas are a little bit more less nice.
Yeah, but you're basically isolating the branches which do the part which do not intersect with each other.
Yeah. Exactly.
So the intersection you are already deducting here,
Yes.
double counting and
Yes.
doing a minus. So whatever your summation is,
Yes.
each term of the summation they are independent, like they are disjoint.
Exactly.
So
This is how we
replicating the tree.
Yeah, this is why it works.
Yeah.
Exactly. So the intuition of why it works is really that you take this back XB, and as I was saying, this is a separator. So this is extremely important. If it wasn't a separator, it wouldn't work. So now you have all these different branches, which they might intersect in the back, but among each other, because there will be no edge. This is because it is a separator.
Yes.
So that's why we can, in some sense, we can glue on the separator and compute the subtrees, and we glue the result here. And that's why it works, because these parts are independent from it. So algorithms for 3D compositions are nothing else of thinking, oh, what happens if I have a separator of my graph? You look at your separator, and you see that how the different pieces interact. This is one way to see it.
So Flo, sorry to interrupt. We have to change the battery. It takes 1 minute.
Shall we do this in time for a break?
You choose when. You
Let's
choose
break,
maybe.
break.
Yeah, it's a good time to stop maybe.
Yeah.
Yeah.
I mean, I just want to give a hint of the proof. Okay. 5-minute breaks.
Sure. Please put in that we are starting.
So everyone, maybe avoid drinking that RO water. He was drinking just now. No, it's not too bad, but don't drink more. Okay. Now someone told me that it's not fully functioning, so don't use it, please. You did not know?
No, I didn't say.
No, but you told me.
No, I told that don't use it.
Okay. Fine. So don't use it, and water is coming. So in the tea break, I think we'll get this.
Okay. Start. Start है सर. बात नहीं करेंगे. Start है सर. बात नहीं करेंगे. Start. Silent, please.
This thing what you're doing, it always gives an optimum.
अब start कर.
But it depends on the composition.
Yes, and the running time will depend on the algorithm.
सर अब स्टार्ट कर दीजिए. बाद में थोड़ा तो कट हो जाएगा. बाद में एडिट करना है तो थोड़ा कट तो कर सकते.
आप ही बैठना पड़ता है.
Of course, yes. The algorithm process will run on the tree, so if the tree is different,
क्योंकि जो कट करना है पता नहीं चलेगा.
algorithm will
Silent कर.
नहीं ठीक है. कोई प्रॉब्लम. वो नेचुरल. Let's start. Yes.
start.
Yes.
Okay,
We are
so
ready. Recording.
Let's start, please. Thank you. So, before I give an idea why this formula should be true, maybe let's analyze now, assuming the formula is true, what is the algorithm? Well, as I said before, you just compute bottom up. So you root, the tree composition is given, or you can compute it using the algorithm I was mentioning. You assume it is given. You root your tree and you do bottom up computation of the functions. See this as one more. So it means that at every node you have so that means at node B you for each S include S's. Of course, well, for each S use the formula. Well, in fact, you have to check whether S is an independent set or not. Because if it's not an independent set, it's completely useless. You set it to minus infinity, but you still have to check this, right? So what's, yeah, and in the end, as I said, at the root, you just take the maximum over all these functions. So what's the running time? So for every node of your tree decomposition, what you're doing 2 to the width. So let's say for t, let's say it has width w. Okay, so you are doing 2 to the w plus 1 function. So remember, the width is the bag size minus 1. How many possible s are there? Number of subsets of the bag. So 2 to the power w plus 1. For each of them, you have to check this independent setting, so that you can maybe do in, bag size squared. This is w and omega. Because you just have to check all the edges, but there is no edge inside S. Squared. Okay, but then you have to do this. Okay. And for this, you have to go through all these possible. So for every child, you have to go through all these possible S primes. So this might be another, plus 1. But these choices are individual, so you do for the first child, then you again for the next child, and so on and so on.
What is this? The next 2 power w plus?
This is for the children. The choice of S prime. So you have to maybe multiply by the number of children. Okay. But again, I can use the same kind of, so if I want to simplify a little bit, I can argue about the edges of my tree decomposition. And I can argue that actually each edge of the tree decomposition will be considered only in the computation for this V. So I think we can put here the number of edges of the tree. And then we don't need to count the number of children. So I think something like this should be true. Anyway, the important thing here is that the exponential part only depends on the size of the bags, on the tree width. So this is from, let's say. Okay, one thing is this tree decomposition. Well, we can assume that it has a linear number of nodes as a function of the vertices of the graph G. This I can say this is, let's say, n, where n is the number of vertices of G.
In this tree decomposition, why you take edges?
Well, because it's just for the sake of counting. When I compute the function at a node, I have to look at the children. So this is like looking at an edge of the tree position. So for each of these edges, I have this 2 to the W. It's W and forgot to say it in that theorem, but remember that we can always, if we have a tree decomposition, I mean, it's not immediate, but at least if you know the partial K-tree form of it, then there are exactly n number of nodes in your tree decomposition. So it's, all these theorems always come with a linear number of nodes in the tree decomposition. Remember that you can artificially blow up the tree decomposition, so you have to be slightly careful of that, but this is always possible. Okay.
Can you explain how do you get the 2 to the power w plus 1 and w square?
So this is the number of s, choice of s. Okay. This is choice of s prime in the child, and this is checking that s is an independent set. You have to do that because if it's, you have to, define this. This is a very minor because it's completely shadowed by this 2 to the power, of course. So I'm just, I mean, you probably can do something more careful, or maybe it's not completely accurate, but the main point is that it will be a function of w being the width, times the number of vertices of the graph. This is the important. Okay. And this is kind of also expected that we get an exponential function. I think I said it before, but because independent set is an NP-hard problem on general graphs, so yeah, you don't want that every graph has tree width n, so you don't want this to be a polynomial in n, it would contradict the NP-hardness. So why is this formula true? Why is it true? So my idea is to try to hopefully give you similar arguments as before for trees. So I think the easy part is the at least part, which is the constructive part, existential part. Okay. So this is just to say that I'll take my S, I'll construct. So I'll construct some S V. So I take S, and for each plus, for each child, I exactly look at this formula. This formula tells me I'm taking the maximum for each child of the S prime, over all the S primes which agrees with the S on the intersection. I take the ones that give me the largest independent set. And so I do this for all the children. So the end and the final size of, so what I get is an independent set. So this is the maybe the important thing to see. That if you do this, the graph continues. Move your S. This is my S. So that it touches the border. Like this. So for any S, I can take any S prime that agrees with S. Okay. This is another prime. This will be S prime 1. And this is the rest of the independent set. And what I'm saying is that, so I'm saying for each child, among all the ones, all the S primes which agree with S, like this one, but there are many others, I take the one that whose formula is the maximum over this subtree, over this subgraph. Now, since this here we have checked is an independent set, important thing is to notice that this part, if you forget about the bag because it's a separator. This part is completely disconnected from each other, these parts. So the union is an independent.
But there can be an edge between S minus S dash and S dash minus S, right?
Like this. You mean like this?
No. S minus S dash and S dash minus S.
Then that is an independent set. We have
Like
checked
this.
this before.
But we know that S is an independent set.
Ah, that's true.
So there are no edges within S.
That's true.
So I didn't get, sorry, what did you say?
There can be an edge between S minus S dash and S dash minus S, right?
No, because you mean here and here?
Yes.
No. Okay, but good point. Thank you. That is true. This is actually necessary. But we know that the lemma yesterday saying that the intersection of the two bags is separate. Very good point. I missed that. So yes, it is true that we don't have any a priori knowledge on S and this part, but because we know this intersection is a separator, we know this edge will not exist. Correct. So you can include, so union like this is okay, and yeah, it is true, union like this is also okay. These are three models. Okay, take S plus for each child. Max independent set of size this thing. I'm just repeating that what it means is. So you take this. So this has exactly size all this. Right? So this is take this. That is an independent set of GB with, which intersects XV exactly in S. Section with XV in S. Okay, and this follows from the separation. Let's see. Okay. So the main reason why this works is because of this separation property that it will be an independent. And it has that size. I mean, this is just looking and counting. Good size. And now, why can we not do something better than that? It is really the same idea as before. Star. Take a largest independent set of your GV. same as before, so you take an optimum one, which satisfies the property that you intersect exactly in S, and you see that for each of these children, what you get is some particular independent set. We don't really know what it is, but something like that. Now, by definition of these formula, well, again, we know that if you restrict to one of the subtrees, what you get is an independent set. But this is completely true because just deleting something from the graph, you are not creating any edge, so of course these parts remain independent set. And by definition of the formula, this part cannot be more than this thing. Well, for a particular S prime. So what you get is this is X prime 1. Consider S star equals to S star intersection GI, E of GI. Okay, so I'm considering for the integration of S now. So I'm putting this part, and the size of Si star is at most what? At most this, I of S star intersection maybe I don't move S star intersection X VI. So yes. So I take Si star, is this thing. S1 star. So I'm just essentially cutting out the other parts. I look at them individually. Since this is an independent set of my subgraph here, GVI, by definition of that formula, I mean, I have no assumption. I don't know that this is optimal or not. So that's why I'm writing at most. It is at most the largest size of such a guy.
So what is
equal?
What is GI exactly?
Sorry, GVI. GVI is that subgraph induced by TVI. Like GV. GV is this subgraph, so you know that the graph continues here. This is GV, so this is GV1. I'm looking at V1 is the first child of V. This is GV1. This is GV2.
So XVI is in the tree decomposition, whatever I have.
Yes, it is
now
the bag of
having
VI.
that root, V as root, whatever is down there, everything.
Yeah. Yes. Okay, so we have Si star this. Okay, so now I think we just have to plug in the numbers. So S star, right, is at most the sum of the Si stars minus the intersection with S. And that, well, I have to count S because I'm going to remove it from each thing. this in. And again, because here I was taking a maximum, here I don't have the maximum, but this is certainly smaller than the maximum of all the possibilities, right? It certainly agrees with S on that intersection, so now you just plug in. What I just wrote, etc. This is a bit tedious, but I forgot the sum. And formally, we need another line to just show that this is at most maximum. But this is immediate, because of course any member is smaller than this. Okay. So the important message here is you always have these two parts of the proof. One of them is existential, saying that, okay, if you have the solutions for your children, you can create a new solution for your parent. And the other one is a bound, which says that actually you can do better. Because if you could do, in some sense, what I'm saying here is that take the optimum, then I restrict to the children, and it will be smaller than the value of the children. You can, if you prefer, you could do a proof by contradiction, like suppose I had a larger one, and then you would argue that, oh, but then one of the children would be larger than the formula, which is a contradiction. I think it's the same. Any questions for this?
So actually, can you define once more with GV?
Okay, so GV, it is the subgraph of my G, induced by the set of vertices, which is the union of all the bags in this part of the tree. Let's have the picture. So you always have to remember this picture, right? That you have your tree composition on one side. Okay, so I said that this is TV, subgraph rooted at B. So on the graph side, it looks like this. This is this bag, this bag, these bags, this. Okay, this is R. This is XB, this is XR, etc. This one, this two. Okay, so what is GV? You take all the union of the bags here, which is induced by, which correspond to the nodes of TV. Take the union. This is a vertex set of your graph, and GV is this red pink graph.
So why that SI star is bounded by I, upper bound of that SI star?
Because this is the largest size of an independent set. This looks like that. This is an independent set. It cannot be larger than the largest. It's at most the size of the largest. This is by definition of the form. Because this is an independent set, which corresponds to this integration.
What is the relation between the A star and SB?
S star and
SB.
well, I just called it S star. What was SV? SV. I mean, SV was just kind of a notation in the definition. Yeah, here it's probably the same as SV. What I call SV in the other thing. Well, it's just that, yeah. Actually, SV was not a very good notation because I was iterating over all the possible S sets. But here I'm taking one optimal one and applying what's the idea of this kind of algorithms? So independent set is easy. So I mean, why? I hope you believe me. This is probably the easiest case among the classic problems. The reason is that why it is nice to start with independent set is because independent set only has interaction within itself. So you just have to check that, okay, there is no edge. You don't care about the rest. So in other problems, you will have to care about also other vertices. You will have constraints. For example, one classic example we can do in the tutorial is dominating set. Dominating set, also you are looking for a subset S of vertices, but you have to dominate all the other vertices. So you have to be careful about that. So it's a bit more tricky, a bit more complicated. Yeah. It's 30. I mean, we started late, so I still have 10-15 minutes. Anyway, the tea break is late if I understood correctly. Well, I don't know today.
They have come.
They already come. Then you will have to wait for the tea break. Okay, what do I want to tell next? Yes, okay. So, one really important tool when you want to make these algorithms even simpler is to use the flexibility of 3D compositions. As I told you, you can play around with these 3D compositions and change them. And one very standard tool for doing that has been called nice 3D compositions. So I don't know if nice is a nice terminology because everybody calls this thing's nice when they like it, but anyway, this term has sticked now, so it's very standard to look for these nice 3D compositions. And this will make these computations easier. So the idea is to take your 3D composition and reshape it in a way that will make all these things much easier. Well, I want to tell you because for the tutorial it might help you to work with these guys. And this actually will show the benefit of using 3D compositions instead of partial K-trees. Now you know that these are equivalent of partial K-trees. The 3D composition you get can be complicated. But we are going to use the power of the flexibility of 3D compositions to get something nicer. So, a 3D composition is nice if okay. So for every leaf V, what we want is the bag to be empty. Okay. This one thing, and otherwise. So essentially what we're doing is we want our tree to be a binary tree. This is the main idea. So we have the leaf nodes, which we want their back to be empty, and the other ones, you can partition them as follows. We have so-called introduce nodes, forget nodes, and join nodes. So what's an introduce node? Let me do a picture, it will be easier. So an introduce node, first of all, it has only one child. xt minus xt prime, like this, will be some vertex x. So what you have is you have so the difference is only 1 between the two. So this one has 1 less, and this one introduces a new vertex of the graph, let's say x. So it's called an introduced node. For get node is exactly the reverse. Prime. And then
Actually, prime minus x, right?
sorry?
Actually, prime minus x equal to bigger than x.
xt prime. Xt prime is smaller.
So where is this extra vertex actually?
xt. It is in xt, so xt minus xt prime is bigger, so it is x. xt minus xt prime should be equal to 1 vertex.
Yes. So then
So that means xt is larger than xt prime. So xt minus xt prime is non-empty. Here it is exactly the reverse. So they basically differ by only 1 vertex, and they have only 1 child. So when I say 1 child, it means exactly 1. And join nodes. Two children. 1 to 2. And so join nodes are interesting. So they are the binary part of the tree. So a join node has exactly 2 children, and their bags are all equal.
Parent bag is equal to both the child bag. Parent bag is equal to the child bag.
Exactly. The 2 children. And
The first thing in the introduced node,
yeah.
xt, you should also include that xt prime minus xt is null set.
Oh, it follows from this.
I mean,
Yeah, you're
xt
right.
prime is
Yes, yes.
inside xt. That's
Yes. Okay, so a better way to write this.
you can write xt prime union x is xt.
Yeah, but that is not true because then they could be equal. I also don't want to
No,
avoid it.
xt prime union singleton set x.
Yeah, if x is already in xt prime, they can be equal. So this is
X is not in x.
yeah. So actually, I wanted to avoid that. That's why I
Okay,
did it. But I yeah. Okay, so let's say that right.
Yeah.
Xt prime union xt plus xt prime. I don't think we can avoid an situation.
You have one other way. Instead of union, you write a box union, so disjoint union. Then,
I don't
then
know what you mean by that.
so instead of this U kind of a thing, you can write a box kind of a thing, which means already the second condition. That they are disjoints.
I don't know this notation.
Okay.
So same here, right? I mean, we really want one thing different. So and this is actually, I think, I kind of already proved yesterday how to get this. You can easily get it. It's not difficult. So one can always. So the lemma is. So this was introduced by Brooks in '94. This does the any decomposition nodes can be transformed into a nice one. Same width, and also all of maybe some W. Not sure. Okay. So well, maybe I don't have so much time. So I think it's almost over. So what's the idea? Well, yesterday I was kind of doing it. Well, in fact, let's take an example. 6. So if I take this tree decomposition, which is given by the 2 tree, I get this. Okay. How do I turn it into a nice tree composition? Well, the first thing I can do, because of the leaves, so I need this leaf. But now I can just trivially do like this. So this, let's say this one. So I am decomposing, I mean, adding little by little. So you see these are all introducements. This is introduce, introduce, introduce. Sorry, forget. Forget, forget. 1 to 4, now I want to go from 1 to 4 to 1 to 3, so I do this, I forget 4. Well, if you look at this, I'm doing reverse, so I'm actually introducing 1, 2, and now I can do 1, 2, 3. Some space. 1, 2, 3. Okay, and now here you see that there is some branching. So what I'm going to do, I'm doing a join node. So I'm copying 1, 2, 3. So what I'm doing is I'm just processing the tree composition like this. And whenever, okay, first of all, these things, I'm basically when I introduce too many or forget too many at once, I just decompose this into a few steps. Okay, so that's why there is this W, because you might have to decompose a bag into W bags because of that. And then when I can see that there is a branching in my tree, I do this. So I do a join node, and then I continue. So, 3, 5. So I have to get rid of 1. So I do this. This is an introduce node. So this is a join node. Sorry, this is the introduce node. Forget. No, introduce. 2, 3, and then I do the same. Arbitrarily until I reach this. And same thing on that side. 2, 3, 5. 2, 3, 5. 2, 5, whatever.
It needs some log.
Huh?
It needs some log if logarithm transformation. If there is so many children around.
Yes, so good point. If there are many children here, I have to transform this into a binary tree of join nodes. So you're right that there will be something. So I have to get a binary tree with that many children, number of nodes 1, 2, 3, 4, 5, 6. So I'll do this, for example. So all of these will be join nodes. They're all copies of 1, 2, 3. I'm just making sure that there are enough children here so that I have enough children branches. So yeah, what exactly the count of this?
Number of leaves will be
Number of leaves will be this. Yeah. So what's the size of the tree? Yeah, it will be the number of these things. Well, I don't think it changes by more than a constant. But okay, anyway, this is the intrusion. So it's just a technical lemma. But now, why this is important? Because now all these DP things we are doing, they become much easier. because now I don't have to consider all these different children. I can just focus on these types of nodes. And these are extremely simple, like this guy has just one child and one vertex difference. Same here. And here, okay, I have two children, but they're exactly the same. So it makes everything much easier. So you see all this business I was doing with S prime, intersection S, blah, blah, blah. This becomes super easy thanks to this definition. Super easy is maybe exaggerated, but it becomes easier.
So how many vertices like this decomposition will be there? Can we calculate?
So, I mean,
size.
Yeah. Yeah, something like that. I'm not completely sure about the numbers here, but you stay linear.
Converting from that to that, how much?
Yeah, so you do exactly what I was doing. So this thing takes, when you do this kind of things, it takes roughly W steps, more or less. Okay, you may have to do it twice. So this is, so one bag you can decompose maybe in W bags, smaller and smaller and smaller, bigger and bigger and bigger. And then you have this business of handling the many trees and transforming this into a binary tree. This, I don't know, you can analyze it carefully, I'm not sure exactly, but it's not something polynomial in linear. Maybe it's a W squared here, I'm not complete. But this is not very important. The important thing is rather that it stays linear, it doesn't blow up.
So even though this is actually far from optimal, no, optimal means, okay.
No, if you had an optimal tree composition, the width stays the same.
Width is the
You have
same.
not increased the bag size.
Okay, okay. The back size, yes. Back size, many bags are there, but the back size is high.
So I think I will stop here. I already extended by 10 minutes. Yeah, so the rest we will
So
discuss in
when do we start the next one?
tutorial.
Yeah, we have 10 minutes to 11. So maybe 10 is okay?
10 minutes?
10 minutes maybe too less.
Yeah, you decide.
So
You decided.
20 minutes break.
Go in the, yeah.
20 minutes break is okay?
Yeah.
So we meet after 20 minutes in that other room.
So 10 past 10 in the control room. 11.
So they are anything you like. Any 3D composition.